So we have an abstract algebra practice final exam. Let's begin. Let G equal the following set of all a plus b square root of 2, and b belongs to z, a minus b congruent to 0 mod 2. Okay, so under addition. Sorry about that. Groups and settings. Part A, prove that G is a subgroup of all real numbers under addition. So groups and subgroups problem here. So we're going to take x equals a plus b square root of 2, y equals c plus d square root of 2, with a minus b congruent mod to 0 mod 2, c minus d congruent to 0 mod 2. Then x minus y equals a minus c plus square root of 2 times b minus d. We're going to check the parity condition, a minus c minus the quantity b minus d. It's going to be equal to a minus b minus this quantity c minus d. And since both a minus b and c minus d are even, their difference is even, and therefore a minus c minus the quantity b minus d is congruent to mod 2. So x minus y is an element in G, and also 0 equals 0 plus 0 root 2 element in G. So G is a subgroup of that real numbers under addition. So that's part A. Part B, determine whether G is cyclic. No, if G were cyclic, then there would be some G equals a plus b square root of 2, such that every element of G is an integer multiple of G. And that means every element would have this form, n of a plus b square root of 2 equals na plus nb square root of 2. So the coefficient pairs would all lie on one integer line, na, nb, but G contains 1 plus the square root of 2 and 1 minus the square root of 2. Their coefficient pairs are 1, 1 and 1, negative 1, which are not integer multiples of one common non-zero vector. Therefore, G is not cyclic. And for part C, find the minimal generating set for G. So here, since a minus b is even and a and b have the same parity, we let m equal a plus b over 2, n equal a minus b over 2 for n. And then for m, where this n belongs to z, and the following a equals m plus n, b equals m minus n, we could say that a plus b square root of 2 equals m plus n plus the square root of 2 times the quantity m minus n. So rearranging that, m times square root of 1 plus the square root of 2 plus n times quantity 1 minus the square root of 2. So therefore we could say here for G is generated by 1 plus the square root of 2, 1 minus the square root of 2, and a minimal generating set is that 1 plus the square root of 2, 1 minus the square root of 2. Okay, so that's number 1. Let's move along to number 2. Let's see if this holds up. Okay, so number 2, we let the z mod 840, the G equals z mod 840. How many elements of order 24 does G contain? For part A, cyclic groups and orders. So since z mod 840 is cyclic of order 840, for every divisor here, for that D 840, there are exactly phi of D, elements of order D. Some people say phi, I'll say phi in consideration of the abstract algebra. For here I'll call this phi. Factor in 840 is 2 cubed times 3 times 5 times 7. Elements of order 24, since 24 equals 2 cubed times 3, divides 840. The number of elements of order 24 is phi of 24 equals 24 times quantity 1 minus 1/2 times quantity 1 minus 1/3. 24 times 1/2 times 2/3 gives us 8. For part B, cyclic subgroups of order 35. How many cyclic subgroups of order 35 does G contain? So here, cyclic subgroups of order 35. A cyclic group has exactly one subgroup of each order dividing the group order. Since 35 is 5 times 7 divides 840, there's exactly one cyclic group of order 35. Some say cyclic, some say cyclic. C, find all possible orders of elements of G. So the possible element orders are precisely the positive divisors of 840, and here are all the possible orders. 1, 2, 3, 4, 5, 6, 7, 8, 10, 12, 14, 15, 20, 21, 24, 28, 30, 35, 40, 42, 56, 60, 70, 84, 105, 120, 140, 168, and 210. And that's number 2. Moving along to number 3. Okay, so number 3. So we have S8 here for number 3. In S8, we define sigma is here the cycle 1, 3, 5, 7, 2, 4, 6, and tau is that cycle 1, 2, 3, 4, 5, 6. Compute the order first of sigma. Okay, so here permutation groups problem. So for A, the order of a permutation is the least common multiple of the lengths of its disjoint cycles. Here, sigma has a 4 cycle and a 3 cycle. So that absolute value there, sigma equals the least common multiple LCM for 3 equals 12. B, write tau sigma inverse tau in disjoint cycle form. So since inverse tau equals tau, conjugation sends each symbol in the cycle of sigma through tau. So we get the following for that cycle 1, 3, 5, 7. We get this, and that comes out to that 2, 4, 6, 7. And for 2, 4, 6, we get the following. So we wind up with, it's going to be this cycle here, 2, 4, 6, 7, cycle 1, 3, 5. 2, 4, 6, 7 cycle 1, 3, 5. Determine for part C whether the sigma and that tau, sigma inverse tau, are conjugate in S8. Well, we could say yes in Sn, 2 permutations are conjugate if and only if they have the same cycle type. Both permutations have this cycle type, this 4, 3, 1, and therefore they are conjugate in S8. Part D, find the sign of sigma. So a k cycle has this sign, that -1 to the k minus 1. So that sign, cycle 1, 3, 5, 7 equals -1 cubed equals -1, and that sign, cycle 2, 4, 6 equals -1 squared, which is 1. So that sign, sigma equals -1, and we could say sigma is odd. Okay, so that's number 3. Number 4. Okay, so H is a subgroup generated by 4. Okay, and inside that Z20, list all left cosets of H. So cosets in Lagrange theorem, since this operation is addition here for H. Okay, we get that H equals that subgroup generated by 4 as less than or equal to that Z20. Okay, and the cosets are here: 0 plus H, 0, 4, 8, 12, 16, 1 plus H, 1, 5, 9, 13, 17, 2 plus H, 2, 6, 10, 14, 18, 3 plus H, 3, 7, 11, 15, 19. So our cosets here: H, 1 plus H, 2 plus H, 3 plus H. For part B, determine the index given there, index of H in Z20. So there are 4 distinct cosets, so we get 4. For part C, verify Lagrange's theorem directly. So this absolute value of Z20 is 20, and that H, order of H, I should say, order of Z20 is 20, order of H is 5, and then we get the following. It's equal to 4, and corresponds to the order. These orders correspond to one another, Z20 and H, and we wind up with a 20 that's verified as 5 times 4, and we're good with that in a condensed notation there for C. Letter D, determine whether this group given here, the quotient group Z20, over H is cyclic. So yes, this quotient has the 4 elements as given here before. I'm sorry, 4 elements, sorry about that. H, 1 plus H, 2 plus H, 3 plus H, and 1 plus H plus quantity 1 plus H is 2 plus H. 3 times 1 plus H is 3 plus H. And the 4 times the 1 plus H, that's 4 plus H equals H. So the coset 1 plus H generates the whole quotient. So therefore, yep, cyclic of order 4. So that's number 4. Moving along now to number 5. So let D8 equal the following. Part A, list all elements of D8, so normal subgroups and quotients. So D8 equals this, and this is a dihedral group of order 8. Every element has this form order, the K or the KS, where K is 0, 1, 2, 3. So D8 equals this set. From the identity element all the way to R cubed S. For part B, show that this N identity element R squared is normal. So that N is normal, a subgroup N is normal if G, N inverse G equals N. If for every G in element D8, since R squared is a rotation by 180 degrees, it commutes with both R and S. So indeed, R squared inverse R equals R squared. Also S R squared inverse S equals S R squared S. And using SRS equals inverse R, SR squared S equals SRS quantity times SRS, which is R to the negative 1, R to the negative 1, and that equals R to the negative 2 equals R squared. So the conjugation fixes R squared. So G and G negative 1 or G inverse equals N. So we could say that N is normal. For part C, construct the quotient group for that D8 mod N. Okay. Here we have the following. It's just going to be that 8 over 2 equals 4 elements. The cosets Rn equals identity element R squared. Rn is R cubed. Sn is S R squared S. And Rsn is Rs R cubed S. So this right here, this D8 mod N, that equals N Rn Sn Rsn. And for part D, identify that D8 mod N up to isomorphism. So in the quotient here, Rn quantity squared equals R squared, N equals N. Sn quantity squared equals S squared, N equals N. Rsn quantity squared equals Rs quantity squared, N. And in D8 here, Rs quantity squared equals identity element, so Rsn squared equals N. And therefore every non-identity element of this D8 mod N has order 2. So we get this isomorphism here. This D8 mod N is isomorphic to Z2 cross Z2. And also isomorphic to V sub 4. Okay, so that's number 5. Okay, and now that's part 1. And I know I went through this pretty fast, just going through these fast so you have a reference for practice. Part 2 is next. Thank you very much.